we can go ahead and get started. So this will be the final discussion. So you guys will have your final exam tomorrow at noon in this room. Aaron will be with you guys proctoring, so it won't be me, it'll be him. Maybe I can start off. Are there any initial questions at the final? I'm sure Aaron's probably talked to you guys quite a bit about kind of what the setup's gonna be. Yeah.
Is there gonna be a 3D matching during the It's gonna be covered? Because I remember that professor said we don't have to fully comprehend the 3D matching, so I'm assuming that it would not appear on the exam.
3D matching, like specifically that problem.
Yeah, but I think he said that we don't have to fully comprehend it, but I'm not 100% sure.
Okay. Yeah, 3D matching isn't done. I'll just go ahead. So, that problem is not on the exam. Yeah, cool. Any other questions about maybe? I'm assuming you guys can bring in your note sheets. Did you say like how many or anything?
Just one.
Just one?
Okay.
All right, cool, fair enough. So otherwise we can go ahead and just jump into the exam review. So the exam review is by far heavily weighted towards the recent stuff. So like the NP completes, just all the sort of complexity side stuff. The exam is cumulative, but again, I'm assuming that Aaron told you guys this, it covers heavily the new material. So I'm primarily covering the new material. If you guys have questions about the old stuff, like the DP or the greedy or whatever else, I'm happy to cover those, but none of that is featured here. I kind of figured you guys had enough of those problems like in the previous units. So yeah, all right, we can go ahead and get started. So can you guys find the Blackboard review problems? Yeah, great, so that's what I'll be going on. And just to give you guys one final note before we get started, this is not like a sample midterm. Like I did not make these problems with the idea in mind of like making a exam style sheet. These are just more like a discussion, like these are covering the topics that we were covering in class. But you shouldn't expect that necessarily the problems on the exam are going to be easier or as the same difficulty of these problems. So, okay, great. So let's go ahead and get started. So problem 1. So I'll go ahead and read it. It says that in class we saw that 3 sat is NP complete, right? So if I give you a CNF where each literal each clause only has 3 literals, this is still an NP complete problem, even with this restricted version of sat. And sometimes people ask like why 3 sat? Well, let's look at the problem of 2 sat. So 2 sat is satisfiability of 2 CNFs. So it's a CNF, conjunctive normal form, except each clause has a maximum of 2 literals per clause. So it's even like a simpler version of 3 sat. And we're going to essentially prove that 2 sat is in P. Okay, so how are we going to do that? So it says that we can express a 2 CNF using this related notion of an implication graph. And so it says, okay, what's an implication graph? So if I give you a 2 CNF, for each variable or literal, like say xi in the 2 CNF, we're going to create vertices in our graph xi and not xi. And for each clause, we're going to create some directed edges in our graph. Okay, so to give you maybe a little bit of intuition, like let's look at the example that I gave, which is this 2 CNF given. So the first clause, it says like not x1 or x2. So intuitively, it's saying that one of these 2 things has to be true. If this is satisfiable, any satisfying assignment to these variables has to satisfy, say, at least clause 1, right? We have to either have not x1 or x2. So basically, what we're saying is, if x1 is true, such that not x1 is false, then x2 has to be true. That's essentially what makes 2 sat in P, is that for each clause, you only have one choice or the other, right? You have to make one literal true or the other one. If you don't make one true, you have to do the other one. So we're going to try and like model that information in this implication graph. Okay. So how many variables do I have in this given CNF total? Close. Yeah, there's also x3, like at the end. Yeah, so we have 3 variables. And it says that we need to create vertices xi and not xi for each variable. So how many vertices total? 6, exactly. So I'll just draw them maybe something like this. So I'll have like an x1 vertex and a not x1 vertex. I'll have an x2 vertex and a not x2. And x3 and not x3. Okay? So someone tell me, like based on clause 1 and based on the rule that I give you, I say for each clause, like say the clause is xi or xj, we're going to create a directed edge, like not xi pointing to xj, and another directed edge, not xj pointing to xi. So with that in mind, based on clause 1, we can draw 2 edges in our graph. So which edges can I draw? So right, so I have not x1 or x2, and I'll just draw the whole formula, and x1 or x2, and the final one is x2 or x3. And I'll no longer be using this marker. Okay, so based on this first clause, and based on the rules that I give you guys, which edges should I draw? Yeah.
Between like each of these variable in the class, draw the edge. This is
Okay. So which ones?
so not x1 and x2.
So you want not x1 to point to x2, like this.
This is like you draw the edges between the variable inside each class and then do a set cover, vertex cover thing.
We're just drawing the graph. Like,
Oh,
don't think about vertex cover yet. Like, I haven't even asked you to reduce anything. All we're doing is just drawing this implication graph.
Okay.
So based on like the what I say, so like for each clause xi or xj, we're going to create directed edges from not xi to xj and not xj to xi. So like for instance, I'll help you get it out. So for instance, if x1 is true, then x2 has to be true, right? Because this would be false, and this clause has to be satisfied, so x2 would have to be true. So what am I going to do? This means that x1 being true implies x2. This is one implication in this CNF. Like if x1 is true, x2 has to be true. Similarly, if x2 is false, then what?
Then that implies x1.
Yeah. Right? Because everyone see like how these implications like have to hold, like just to satisfy clause 1. I'm going to draw these edges in my implication graph. So x1 is going to point to x2. So x1 kind of implies x2. Similarly, not x2 implies not x1. Okay. So let's keep going. Let's go here. So if x1 is false, then what?
x2 is true.
Yeah. And similarly, if x2 is false, implies x1. Yeah. Does everyone agree with the next 2 edges? These are now based on clause 2. Okay. So I'm gonna draw these edges. So not x1 is going to point to x2. And not x2 is going to point to x1. Yeah.
You just change the or to an implication, right?
I mean, so I'm looking at this clause. I'm saying that I have to like the x1 or x2 has to be true. If this formula is satisfiable, then this clause has to be satisfied, right? So therefore, if I don't satisfy it with x1, then I have to satisfy it with x2. That's what I'm encoding in these implications, right? If x1 is false, then x2 has to hold. And similarly, if x2 is false, then x1 has to hold. And I'm just kind of going along the line, each individual clause, writing all of these like implications. Okay, so similarly, let's look at the final clause. So not x2 implies x3, and not x3 implies x2. And we can finally draw these guys. So not x3 implies x2. That would be this edge. And not x2 implies x3. That would be this edge. Okay. Amazing. So this is my implication graph for this given formula. Yeah.
Can you explain again why not x2 implies x3?
So now I'm looking at clause 3. So this is x2 or x3.
Oh.
And so this, yeah, sorry. It's kind of hard to read. So x2, yeah, my bad. Yeah, and this is also true, right? This is a CNF, right? So inside the parentheses is only ors, and between the parentheses is only ands, right? So we're relying on that for this problem. This is in CNF form, conjunctive. Okay, I told you guys that this is satisfiable, right? So for instance, can someone give me like a satisfying assignment to this formula? Like, give me what should x1, x2, and x3 be?
If you set x2 to be true, then just do whatever you want.
Oh yeah, x2. Is x2 just in all of the class? Oh, x1. Ooh. I wrote it down. So these should be flipped. That is a useful piece of information. So let's just edit. Let's just make some edits in our graph a little bit. Maybe we should just remake it. Okay. Okay, so we have x1 pointing to x2, not x2 pointing to not x1. We have not x1 pointing to not x2, and x2 pointing to x1, and then not x2 points to x3, and not x3 points to x2. There we go. Yeah. So in the document, you will see that there's a negation sign there that I forgot to use. Okay. Great. So now with that in mind, how can I make a satisfying assignment to these? Just like eyeballing it. I think we can still pick x2 to be true, and then now all we have to do is focus on this middle clause, and so we can also make that true by picking x1 to be 1. Maybe say x3 to be 0 or something. Doesn't matter. This should be a satisfying assignment. Okay, so now that was part A. Is just to draw the implication graph. Just make sure we understand like what these things look like. Part B says, using implication graphs, I want you to describe a polynomial time algorithm to decide whether a given 2CNF is satisfiable. So again, we already have seen that 3SAT is NP complete. We cannot solve, well, not that we know of, we don't have any polynomial time algorithms for checking whether an arbitrary 3CNF is satisfiable. But I want you guys to think about how could you, if I gave you a formula, and hopefully everyone agrees that I can build this implication graph in polynomial time, right? I can build this can be built when I say polynomial time, what do I mean in this context? Like polynomial time in terms of what? Polynomial in what? What's like the input for this? For building this graph? Yeah, like it's this formula right here. Like it would need to be polynomial in terms of the number of variables and the length of the formula, right? If it's like a length m formula, or if there's m clauses or whatever, then this would have to be polynomial in like n and m, for instance. Yeah, good. Okay, cool. So what would happen to the implication graph if this wasn't satisfiable? Like that's what we're trying to think about. We're thinking about like, hopefully if this formula is satisfiable, this graph will or will not have certain properties. And same thing if it's not satisfiable, this graph will or will not have certain properties. So for instance, like maybe you think cycles or something. Like we've seen a lot of problems this semester where like it kind of boils down to cycle detection in some graph, right? We've seen problems like that. This happens to not work, right? We can already see that there are cycles, for instance, like from not x1 to not x2, and then not x2 back to not x1. So it's like a little bit different than cycle detection. But yeah.
Can you check if there's edges between x1 and not x1, or like, I guess variables in indication?
Yeah, exactly, right. So like the idea is that if you had some sort of, if this was not a satisfiable formula, there would be some sort of contradiction in the implication graph. And what would that look like as you described? You said edges. It's a little bit like more broad than that. It's just to be any path, right? Like that would be a big problem, right? So if I had, say I started at vertex x1, or maybe we'll start at vertex not x3, just because there's a longer path. I know that if not x3 is true, then that would imply that x2 is true. And similarly, if x2 is true, that would imply that x1 is true. But from here, there's no way of getting then back to x3, right? There's no reasoning for if not x3 is true, then x3 has to be true, for instance. That does not happen. Whereas that would happen if this was a not satisfiable formula. Now you have to be a little bit careful, right? Because just because if not x3 implies x3, it could be that the satisfying assignment picks x3 to be true. So you have to be a little bit careful with that. But how can I check for paths like that exist in this graph? Like what would be my algorithm? Just assume for the sake of argument that we've boiled down this problem, and we really have. We've given the argument is that satisfiability in this formula comes down to checking paths between the vertices and their negations in this graph. Yeah. Exactly. Yeah. So like all I need to do now is just run BFS. Like you can just run it on all the nodes, for instance. Right? Like we've done search algorithms. We just run the search algorithm on all of the nodes available. So that's what we're going to do. Is the solution becomes, so step one is like build the implication graph. And this takes, we said, polynomial time. Step two is to run BFS on every node. And we're essentially checking for paths that look like this, where there's some xi that has a path, a directed path, that leads us to not xi. Or similarly, it could be of this form, where not xi implies xi. And if in the graph both of these happen, then there cannot be any satisfying assignment, right? If xi implies not xi, and not xi implies xi, that's just a contradiction, no matter what the value of xi is. So if this happens for even a single I, so I'll say the formula is satisfiable. The formula is satisfiable if and only if there exists an I where both of these hold.
I didn't catch what you were saying when I was coming in, but did you say these types of problems would be like similar with the example?
Yeah, I think this problem would could be doable. Like I gave you a lot of lead up, I guess. It would be a long problem, because you have to read through all of what is an implication graph. But I think this would probably be attainable in an exam if I gave you hey, here's what an implication graph is, and then I just asked you how do you use this to check whether or not a formula is satisfiable. I think it's about the difficulty. Maybe it's a little bit too in depth, but I don't think this is too much harder than an exam type problem. But I also want to just make sure that I didn't make this review as a practice exam. This is not a practice exam. There are problems on here that are maybe too easy, too hard. It's just to practice the concepts. So yeah, there may be problems on here that aren't quite exam style.
So can you explain again why the formula is satisfiable if we have both of these paths, like xi?
It's not satisfiable.
It's not satisfiable.
Right, because these paths, these really are implications. Because that's the somewhat nice thing about having a 2 CNF is that for each clause, you have to satisfy one or the other. So if you don't satisfy one, then you have to satisfy the other. What this corresponds to, if you have both of these paths, what that means is, suppose you were trying to find a satisfying assignment where xi was true. If xi is true, then that implies that it means that somewhere along the line in this formula, there's a series of implications that say that actually, to make another clause satisfiable, xi has to be false. And this is saying, well, what if xi is false? Then that implies that somewhere along later for some other clause, xi would have to be true. So there can be, if both of these happen in the implication graph, there's no satisfying assignment where xi is true or false. So and those are both of your options. So yeah.
So in the third statement where it says formula is satisfiable, that is only there's not.
Right. So if there's no i's, this is a part of the proof that I'm not really covering. I'm not going super into detail about, but it is true. If there's no I, that's where both of these hold, then you can get a satisfying assignment. And that is, I'm sweeping a little bit of dirt under the rug into that part of the proof. But yeah. Yeah, I'm more so just introduced this because I think it's an interesting problem, and I think it sheds some light onto the fact that 2SAT is an interesting problem. It's not immediately clear that it's not NP complete, but 3SAT is actually the first instance where satisfiability becomes NP complete. And we've seen 3SAT and 4SAT, 5SAT, all of those are NP complete, but it dies at 2. All right, great. So that was just a little bit of a kind of warm up. Now we're going to get into our reductions. We'll start off pretty slow. So we've seen the independent set problem, right? So let's so we have independent set. Someone tell me what the independent set problem is.
Graph and in integer k find the subset of S be such that cardinality of S is greater than k and there are no edges between two
So you're given a graph G, an integer K, and I want to know if G contains an independent set of size at least K, where an independent set is a set of vertices that do not share a direct, they don't share an edge between two vertices. So just to be clear, so problem 1, so these are this is our base problem. Now these are our variants. So variant 1 is connected independent set. Okay, and you can read the description, but given a graph G, an integer K, determine if there exists an independent set of size K that is connected in the original graph. So that sounds a little bit strange, like an independent set being connected. But yeah, also all it is just this base problem with the additional condition that the independent set be connected in the original graph. So like for instance, let's do something simple. Here's a simple graph. Can someone give me an independent set, like the biggest independent set that there is in this graph?
Just 2.
Yeah, just pick like any 2 of the corners, right? Because you can't pick 2 that share an edge. Okay, so this is a very simple independent set. Notice the independent set, it's independent in the sense that there's no edge sharing, but it is connected in the original graph, right? Like you could have an independent set that doesn't share any edges, but the nodes are still connected, right? That's possible. So just to be clear, so that's the first problem, is this NP complete or not? I said that one of these variants is NP complete and one of them has an efficient algorithm. So problem 2 is independent set on trees. So again, this is just an independent set problem where instead of given a graph, you're guaranteed to be given a tree. And the question is, which of these is an NP complete and why? I realize that one of these is actually in the lecture notes, if anyone remembers. You are nodding your head. Which is in the lecture notes?
2.
Okay, yeah, 2 independent set on trees. And do you claim this is NP complete or easy?
It's easy because we just use the algorithm on quiz 3.
Yeah, exactly. So so number 2, this is actually in P. This is in polynomial time. We studied this problem when we were doing greedy algorithms. So this was actually your quiz 3 problem, right? If you remember, where you take a node and then you like delete all of the neighboring vertices. Yeah. Okay, so independent set on trees, this is NP. This is a problem that we have seen before. So even if we've seen even if you tweak a problem just slightly, you are in danger at least of taking an NP complete problem and turning it into something that's NP, even just a slight tweak, like changing graphs to trees. Okay, so now I claim that connected independent set is an NP complete problem. So now I want to do a reduction. Okay. So I will call this, maybe we'll call it CIS. This would be IS. Okay. So I want to prove my goal is to prove that CIS is in NP complete. what direction should this reduction go? So I'm going to do a polynomial time reduction, right? Which side should independent set go on, and which side should connected independent set go on? Remember, so you guys are going to be doing reductions on your final exam. Hopefully it doesn't come as a surprise that you're going to be doing reductions on this final exam. There's going to be potentially more than one reduction even. So given that knowledge, one of the classic mistakes, as we've already talked about, is reducing the wrong direction, right? You're trying to show that some problem is NP complete. First, you prove that it's an NP, and then you do your reduction the reverse way. You take some NP complete problem, and you reduce the problem that you're trying to show is NP complete to the other problem, right? It's the backwards direction. So, which direction should my reduction go here? Which goes on the left?
CIS.
We got some mixed. I luckily I gave it enough time that I actually got in some other answers. Okay, I have more answers for IS, and I agree. So the way that I usually try to remember this, and so CIS goes over here. Usually when you're trying to prove something is NP complete, it's equivalent to showing that it's hard. Like you're trying to show that it's hard to compute. And so if I'm trying to show this is really showing that CIS is harder, polynomially, we don't care about polynomial factors, but it's harder than independent sets. So it kind of gets on the bigger side. We're going to try and take a problem in independent set and reduce it to connected independent set. Okay. I guess we'll show that CIS is actually in NP at the end. I guess we'll do it in reverse order. So we'll do our reduction first. So again, if I'm doing this direction of the reduction, I want to start with a problem in independent set. I'm starting with the independent set problem, and I'm going to turn it into an instance of connected independent sets. So given G and asked if there is an independent set of size at least k. So we're given G, and we're asked if there's an independent set of size at least k. And we need to come up with some sort of reduction, some sort of polynomial time reduction to a connected independent set problem, where again, we're just asked if there's a connected independent set of size at least k. I claim that you don't have to do too much work. This is our first reduction of the day, and I claim maybe not easy to see, but it's easy to explain.
If G is connected, then they're the same.
Yes, I agree. So that's a great thing to notice, is that if the original graph, if the entire graph is connected, then any independent set will be a connected independent set, right? So if I guaranteed that the graph was connected, wouldn't be a problem. But you're not guaranteed. Like you could be given a graph. This G could be disconnected. But I think you're on the right path. You could make it connected, yeah.
We can make it connected by adding a component between
Two edges? If you're saying if you have two connected components. You're saying if there's like two connected
If there were
components.
two disconnected components, you can connect the two. If there's more disconnected components, you like connect the balls.
Okay. You're in the right direction. However, I'm not. So does anyone see a problem with that solution? He says if there's a bunch of connected components, like suppose this is one connected component, this is C1, and then suppose you have C2, and maybe you have C3 or something, and these are all your connected components. And first of all, we can find these in polynomial time, right? We have already discussed way earlier in the class how to find connected components in polynomial time, right? You can just do like your search algorithm and stuff like that. And he says, okay, I can edit this graph by like just taking a node or something and connect it here and connect it here. And then maybe if you want to connect these connected components, then maybe you make another node. We'll actually connect it. Something like this. And connect the graph this way. What's a potential problem of going about this route?
You could add like more nodes so that it might potentially think of
Yeah, like you're adding a lot of nodes here, and it could affect like the independent set that exists. Like if there was an independent set before, there could be like a much larger independent set now. Like you could include maybe some of these vertices in your independent set. But you're closer. You're even closer than Eric was. You're like going in the right direction, I guess. Rather than adding multiple nodes, what can we do? Is that a hand?
Yeah, just one
Okay.
connected to every other node.
So what I'm instead gonna do is I'm gonna make the graph like even more connected. I'm gonna make it extremely connected by adding a universal sink or source node. And this node is just gonna be connected to every other node in the entire graph. So let's do this here. So I'm gonna add one sink node connected to every other node. And there's a really large benefit to doing this. The first benefit is that it definitely makes the graph connected, right? So we're benefiting from Eric's suggestion of, well, if the graph's connected, then it's just the independent set problem, right? So I'm making the graph connected purposefully. The other benefit is that what's true about this node? It's never in a large independent set, right? If this was in an independent set, it would have to be an independent set of size 1, right? Because this is connected to every other node. So essentially, this makes the graph connected while simultaneously not affecting independent sets. So I'll say sink can never be in an independent set. A non-trivial independent set, right? Yeah.
So the reason the other method didn't work was because you could make new independent sets, is that why?
Right, yeah, like, first of all, maybe it does work. Maybe with a little bit of extra legwork, like, you could make it work. However, if I say I add a node for each, like, if I have k independent, m connected components. Suppose I added m vertices to like chain them all together, essentially. I've added a lot of nodes that aren't connected to a lot of other nodes. Like every one of his suggestion was to just have 2 edges. This could and probably will change the size of the biggest independent set of the graph. Because if I had like, yeah, I mean, I don't have any hard examples here, but like you could include these potentially in other independent sets to make them even bigger. Like it could be that the original graph had an independent set of size k minus 1, such that the answer should be no. But then when I do this change, maybe I've bumped it to now over k, and now I'm in trouble because I'm saying that there is an independent set when there really shouldn't be. Yeah. And again, so there are lots of different reductions. If you came up with some other reduction or if you had some other method, could easily work. This is one of those units where there could be many, many different solutions. We'll see some later on where I think there's multiple different reductions that are all valid. Okay, cool. Oh yeah.
Yeah, to keep a runtime for your reduction.
You should just argue that it's can be done in polynomial time. So for instance, this reduction is like done in linear times the number of vertices. I'm just adding one node and then adding an edge to every other node. Yeah, so this reduction is definitely in polynomial time. You should address why is it polynomial time, but you don't need to address like it's O of n, right? Like you don't need to like worry about like specific hard values. Yeah. With that in mind, don't just say it's polynomial time period. Like explain why too. Like yeah. But,
Oh yeah, that's
yeah. You should explain why. I would say that as is generally true, this may not be a perfect proof on an exam, because I say things that I don't write, right? So like,
What would be a perfect proof?
well, maybe you should, so you should say like, this can be done in polynomial time or something, like, I mean, if you really want to be precise, you could say in O of n time, so polynomial or something. And you should, or say, and then something maybe along the lines of, if, how would you phrase it? You would say there's an independent set there's an independent set of size k in the original graph. And you can also name these, like, so usually the original graph is G. If you want to come up with a new graph that has some other properties, I call it G prop or something. That's common notation. So there's an independent size k in the original graph. If and only if there's a connected independent set in the new graph. And the reason is really because the sink that we added won't affect the independent set. That's why.
Do we have to like show the if value between the two solutions on an exam? Like, or do we just say it?
If it's not like blatantly obvious, you should explain it.
Okay.
Yeah, like this is really a big part of the proof, I would say, is that a solution to one is equivalent to a solution in the other. That is a necessary part of a reduction. So sometimes it's more obvious than others, and finding that balance of like how much explanation do you really need for full credit, it's a very gray area, obviously. Like, it's up to the grader, it's up to you. But like, you're never gonna be in trouble by explaining all of the ideas that are in your head as best you can, right? Like, if you're ever in doubt, include it. Like, it's not gonna hurt you.
So on the exam, when we're trying to explain that something is MP, and we start like, oh, it's verifiable in poly time.
Yeah.
So the way to be able to do that, I guess, like most specifically without like missing anything, like if we have to like iterate through nodes, maybe use like something like EFS, like explain how we would like prove it, or
Yeah. So like, for instance, we'll do an example here. So I'm gonna erase the graph. Yeah. So we didn't actually show. We showed that it's NP hard. We showed that any problem in NP reduces to it by showing that independent set reduces to it. We did not yet show that it's actually in NP, which again is usually the easier part. So we'll show. Right. So this boils down to showing that if given a potential solution for the connected independent set problem, that we could verify whether it's a solution or not in polynomial time. So given what would a potential input or a potential solution to this problem look like? What would the form of it be? What would it be? Yeah.
Graph.
I mean, we already have the graph, so it would just be like the vertices, like, yeah. So like, right. I'm just thinking about like just the solution. The solution would be the independent set or the connected independent set. So it would be a set of it's going to be a set of vertices. Presumably, it would have at least k vertices, right? If it didn't have k vertices, then we could just immediately say no, right? Because we're looking for a connected independent set of size at least k. So we can assume that it has at least k vertices. And we need to check whether or not this satisfies the properties of being a connected independent set in polynomial time. So what do I need to check?
You check if it has a path to all other nodes.
Right.
in
So
the
I
set.
so I should check to make sure that these vertices are connected. That's the first thing. And how can I do this in polynomial time?
Also for running BFS.
Yeah, just run BFF. This would be plenty on an exam. So if you just say like, we need to check that they're connected, run BFS. We all know BFS is polynomial time. Like, you don't need to say more than this, but you should be clear. Like, yeah. Okay, 2. What else do we have to check?
It's greater than k.
Okay, sure. Yeah, check that they're. I wrote it as k, but yeah, we should definitely check to make sure that the vertices that we're given there's at least k of them. So
You also have to check if there's edge between.
yeah, I need to make sure that this is actually an independent set, right? I've checked that it's connected, and now I need to check if it's an independent set. So check if S is IS. Check if it's an independent set.
Okay, cool question.
Yeah.
So if we just say check if S is IS, would we get full credit for that? Or is it like
Maybe
too
not.
vague?
Maybe not. Yeah, maybe yes, but maybe not.
So it would be better if we say like check if S has like no other edges connected to it. That would make it not an independent set or something like that, like no extra nodes, whatever.
Yeah, so like maybe you just like give a short algorithm for how to do it, and if it's clear that it's in polynomial time, then maybe you don't have to say. But if it's not clear if it's in polynomial time, then argue it. So like the way that I would probably check is just check all of the adjacent nodes to each of these. So like maybe just check the adjacent nodes for each v sub I sub j. So for each one of these vertices, I'm just going to loop over all of the nodes that are touching it and check if any of them are in this. Right? And this definitely takes polynomial. This I can say like takes polynomial. If you wrote something like this, you wouldn't have to say more. Like it's pretty clear this is in polynomial time. It's just the degree of each of the vertices. So,
So, for question for number 2, can we argue that if S is not greater than or equals to K, then it's definitely an independent set in the problem? Like, other than clearly explicit stating 3,
Yeah.
could we argue from 2 if S is less than K, then there's an independent set?
If S is less than K, then we would just say this is not a valid solution. Because we're asking for a connected independent set of size at least K. And all we're talking about is verification right now. We're trying to just prove that it's in NP. So all I need to check is this a valid solution? And a valid solution is a connected independent set of size at least K. So if this condition is not met, we say nope, not a valid solution.
So we can argue that since we have a set of like S set of vertices, and if it's less than the number of like vertices, then there is an independent set in it.
If it's less than the total number of vertices?
Because I was my point is I was trying to use 2 to just form 3, other than clearly stating 3.
No, I don't think you can combine these. Yeah. If you want, we can talk about it after too, but I think these are just independent. Like you have to check in each of them individually. Yeah. Okay. Yeah, cool. So hopefully it's clear, like BFS, just checking the size of the set, like all of these things can be done in polynomial time. So yeah, verification is done in polynomial. Yeah.
Question about the determining like, or I guess stating if like one's has a solution to the other, then you have a solution to the other one.
Yeah.
Is there like a specific direction you're supposed to go, or?
It should be both directions, right? Like
Oh,
this isn't, it's if and only if.
Right. Okay.
Right, so like, if it helps you, prove both of them individually. Say, if there's a solution to the independent set problem, then that implies a solution to the connected independent set problem, and go the reverse direction. Say, if there's a solution in my new fangled example, then there is a solution in the original. That would give you the if and only if.
Did we prove it for this one?
Not explicitly. It's pretty clear just by the fact that the sink, there's two facts that in combination give you this.
Right.
The first is that what Eric said, which is that if the graph is connected itself, then the connected independent set and independent set problems are just the same problem. That's part of it. The second one is that adding the universal sink cannot that sink node cannot be in any non-trivial independent set. Those two facts together basically just give you this for free. Like I think that you don't really need to say too much.
Yeah. So like as long as you have the reduction and you explain why your reduction works, you just state it.
But again, I mean, I don't have, unfortunately, I don't have time to write all of the things I just said to you. And that's why sometimes one of the things I write on the board may not be like a full credit answer, because I don't have time to write it all out. Yeah. Okay. Moving on, I think. Yeah, we don't need to talk about 2. We've already done 2, like the greedy algorithm. So. So 3. So this is now, last 2 problems were problems I wrote. These are now textbook problems. So these are somewhere in chapter 8. I didn't write down exactly where, but yeah, these are now chapter 8 problems. So it says for each of the 2 questions below, decide whether the answer is yes, no, or unknown, because it would resolve whether or not P is equal to NP. So there are certain questions that if we knew the answer to, it would either tell us P not equal to NP or P equal to NP. So we start off by introducing a problem. So let's just, we looked at this interval scheduling problem, right? We actually looked at like many different iterations of the interval scheduling problem, I think, probably maybe too many in guys' eyes. This is just the basic version. So like unweighted, you're just given some intervals overlapping and you're trying to select the largest subset of them. This is the decision version of interval scheduling. So given a collection of intervals on a timeline and a bound k, so integer k, are there at least k intervals that are not overlapping? Basically, that's the problem. So it's like it turns the interval scheduling problem into a just yes or no, are there at least k or not problem. Okay, and this asks whether or not. I think I'll erase question 1, but if no one wants to take a picture. Okay, yeah. I will post the solutions to this tonight too, so if that changes your feelings, then so be it. And if I don't, someone email me. So I know that you guys need this like tonight. Like tomorrow is not helpful. So. So problem 3. So given this decision version of interval scheduling, is it the case that interval scheduling polytime reduces to vertex cover? And just so you know, vertex cover was not chosen. It was completely arbitrary. This just could be any NP. So I'm saying, is it true that interval scheduling, polynomial time reduces to SAT or vertex cover or whatever you like, whatever you want to think about, and why? I promise you don't have to actually do any reduction. Like, if the answer is yes, you can just say why. You don't have to actually tell me what the reduction is. If the answer is no, then you should have a reason, some reason for that. Yeah.
Sure, because you can just use the vertex cover like algorithm for the answer with solve it.
In polynomial time.
Yeah.
Yeah, that's also true. The key idea and the solution that I would give is, well, interval scheduling. This is in P, right? I like your answer. I'm going to use it. I'm going to use it for the next question. But this is in P, right? So with this, what is it also in? What is P a subset of? You guys don't know that many, like you guys don't know that many classes of problems. So there's only so many answers that can go here. NP. Thank you. Yeah. So we should note that like any problem in P is gonna polytime reduce to any NP incomplete problem, right? Because any problem in P is also a subset of NP. Any problem in P is also efficiently verifiable. And vertex cover is any problem reduces to vertex cover. Any NP problem reduces to vertex cover. Polynomial. Right? Okay. So if the problem itself is solvable in polynomial time, then definitely we can reduce to any NP. Okay, let's move on to B. What about the other direction? Can I reduce vertex cover to this decision interval? I see no.
Say no.
You would say no or definitely no?
Definitely no.
Okay, but you're close. Yeah.
Would that mean that if this was true and P would equal P or no?
P would equal NP. Yes. So if true, I agree. And I agree with that, right? Because this is a polytime reduction. Vertex cover is reducing to something that we know is in P. Right? Okay. So the answer then is not quite false, right? Because we don't know that this isn't true. We strongly, strongly believe this not to be true, right? We strongly, strongly believe that P is not equal to NP. We are not certain, and we don't know if this is true or not. So this isn't what yet.
So if it's false, does that make P not equal to NP?
Okay, that's another question that we could talk about. I'm gonna delay that for at least a little bit. Yeah.
Why is the rate greater than equal to sign flipped?
I just because I didn't want to rewrite everything.
Oh, okay.
Like I would have to just read.
Okay, so we're basically past the first part where we're
Yeah.
trying to. Okay.
Yeah. You can always just write it
Oh, okay.
this way. Yeah. Just
Just making
I
sure.
wanted to use as few brush strokes as possible.
That's fine.
Yeah. Okay. So-
Excuse me.
Using his argument he said for this one, could we say there's no answer because whichever we choose, we could say P is equal to P or P is not equal to N.
So right. So definitely true that if vertex cover polynomial time reduces to interval scheduling, then P is equal to NP. Or right. If your question was if vertex cover does not polynomial time reduce to interval scheduling, does that mean that P is not equal to NP? And I think that you cannot say that.
Sorry, isn't the question asking for interval scheduling reduced down to vertex? Like, or aren't they flipped?
We're on part B now.
Or part B? Oh.
Yeah. So part A was just that was true because interval scheduling is in P, which is a subset of NP. So yeah, so this is now part B. Yeah, I probably should have been a little more explicit, but yeah. Yeah, I think the answer is no. I think it's not an interval. I would need to think about that outside of right up here on the board. So I want to think about it a little bit harder, but I'm pretty sure the answer is no. Okay. This is pretty quick, but any questions about this guy? It's just one of those kind of quick problems at the beginning of the chapter. Right. We have until 1:40 today, right? Like, not until 2. Yeah. All right. New problem. I think I'm probably just gonna erase this guy because there's so little. But just so we're clear, so this is the final answer is that we're not sure, right? We don't know for certain one way or the other, because at least one of the directions would result in a solution to some p%.
It is true that interval scheduling does reduce.
Oh wait, no, this I think you are right. I want to I don't want to present it. It's not sure, but yeah.
I have a question. So
Okay,
in
yeah.
NP, does that mean we just have two subsets of P and NP complete? We say that?
Say it again.
Instead of NP, just two subsets.
This is NP, okay?
It's NP complete and P. Is there a problem that is not P and neither NP complete?
Okay, so you're saying we have this.
Yeah.
And you're saying, is there anything in here
Yeah.
that's not NP complete, but also not NP?
Yeah.
That's a great question. So the first thing is that we don't even really know if these are different, right? That's the first thing to state. We are not certain if NP complete and P are different. If P is equal to NP, everything becomes the same. However, let's assume that P and NP complete are different, that P is not equal to NP. There is a class in between. Can anyone guess maybe what this class is? It's an NP. It's harder than P, but it's not NP complete. It's actually provably not NP complete. There are problems that we know are here. NP hard is like here. This is NP hard. So it's a good key point. So NP hard is like NP complete is in NP and NP hard.
Oh, that's why for something to be NP complete, it has to be both.
Yes. NP complete is defined to be the intersection of NP and NP hard.
So like when you think of a Venn diagram, it's
Yeah, exactly. Like, yeah. Couldn't have said it better. But there is something in the middle, yeah.
NP intermediate.
Yeah, exactly. This is NP intermediate.
really creative names.
I know, yeah. Yeah, so there are problems that are in NP intermediate. I believe that factoring is in NP intermediate. If you wanted like an example of a problem that is not NP, and one of the reasons why the encryption and stuff works like factoring is you will have to take probably like Aaron's complexity class or something if you want to learn more about that. Yeah.
Does that stretch outside of NP?
NP intermediate.
Yeah, I guess I'm confused. How can you provably say that a problem is not NP complete?
I think it relies on the fact that P not equals NP. Because if P is equal to NP,
Right.
everything collapses onto itself. Yeah, so you can't say this is definitely not NP, but people, okay, in research, people assume way crazier things than P not equal to NP. Like people publish papers under the assumption that P is not equal to NP.
I have a question. So since we're usually going under the assumption that P is not equal to P, why is it that for like part A we could just say like, well, if it is true that P is equal to NP? Like, shouldn't we like,
Part A?
yeah, was that not the answer? Like
Part B.
part B? So for part A, the answer was,
Yeah, part A, the answer was yes.
the answer was yes, and that was because we were saying that P is within NP.
Yes. P, no matter what, P is a subset of NP.
Okay.
Because P is things that are efficiently solvable, NP is things that are efficiently verifiable.
Oh,
So inherently, if you can solve it efficiently, then you can definitely verify whether a solution is
so
positive.
if it's already like, if P is already a subset of NP,
Yes.
then why is, I don't know.
Like why is this?
Why is the assumption that P is not equal to NP then?
It's strict versus not strict subset. Like I know this is known. This is trivial. Like
Yeah.
this is just obvious. But it's not known whether this is strict subset. This means that like there are some things in NP that aren't in P.
Oh,
Right. So it's like all circles are squares, but not all, or all squares are rectangles, but not all
Yeah.
rectangles are squares, sort of thing. This is saying I know that P is a subset of NP. The question is it a strict subset? Is this a smaller or equal? Is it smaller or is it equal to? We don't know. Yeah. It's definitely not bigger. It's in no world is P ever like larger than NP. Yeah. Yeah. Okay. Yeah, great question. Yeah, I mean this is like it's too good of a question. It's not covered in this class because it's too complicated. Yeah.
So like the emphasis, what we need to know to answer number 3.
Yeah.
Was basically to understand like the relationship P and NP.
Right. Yeah.
Subsets.
Yeah, and also like just to give you an example of like we've done a lot with NP complete problems and reducing NP complete problems to one another, just to show you that okay, let's just make sure we're all on the same page. Like all of the algorithms that we've studied so far, these all reduce to the NP complete problems. Like those are all easier than the NP complete problems that we've been studying. So if you just take some algorithm that we solve with greedy, like interval scheduling, it's not even an NP complete, but you can still do a polynomial time reduction because everything in P, you can do a polynomial time reduction to anything in NP complete. Yeah.
And B was false, right?
B is unsure. Yeah. Right. Okay. I want to think about your question. You asked if it's not true, if independent set does not. Yeah, that would give you that P is not equal to P. Yeah. Right. For a similar argument as you just did yourself, like if you can't do it, then that means that there's no polynomial time algorithm. Yeah. Yeah. Sorry, I don't know what I was thinking earlier. Yeah. Yeah. So this question technically, like part B, is equivalent to P versus NP. Like a solution in either direction would give you an answer to P. But don't spend your Friday night trying to solve it, please. You won't get very far. Okay. Great. So this is 4. So this is a question that assumes that SAT is in P. So like for the next two parts, we're gonna assume that there is a polynomial time algorithm for SAT. This is something that is generally not considered to be true. Okay, so suppose there's some algorithm A which solves SAT in time n to the C for some C. And we've already seen that SAT can be reduced to or from any NP complete language. But suppose SAT is in P. So this is for A. And we're probably going to skip for B, just so you know. But suppose SAT is in P. Does this guarantee that SAT will reduce to any other problems in P? Like, does this guarantee, for instance, SAT polynomial time reduces to, and again, I just chose a random polynomial time algorithm for this, but say max flow. Look at max flow. This is a polynomial time algorithm. This question would be the same question if I replaced max flow with interval scheduling or some other problem in P. If SAT is in P, does this mean that this reduction exists?
Yeah, so yeah.
You say yes. Why?
Due to the fact that we can reduce SAT to max flow, and if we can reduce SAT to max flow and SAT is within P, then obviously we could solve any problem in NP.
But I'm asking about like whether or not this reduction exists.
No, that reduction actually doesn't exist.
If SAT is in P, if I guarantee you that SAT is in P.
It's kind of confusing because
It is very confusing.
in my brain I know like SAT is NP complete, and I know max flow it's it has a polynomial time.
Yeah.
I'm trying to make an argument for two things.
Yeah, I'm just gonna briefly cover this because yeah.
Is it true?
Okay, why? He says true. He's correct.
It's like essentially what you're saying is like you're changing like SAT into max flow, and if SAT is in P, then since we know max flow is also in P, then we can just reduce it and then have a polytime solution.
I actually liked what you said for part 3, where you said just yeah. So what you said for question 3 was you said if SAT, like in this case, if SAT is in P, that means there's a polynomial time algorithm for SAT. I don't want to go too in depth into the proof because it's maybe not the most important. I think we can spend our time on the rest of this more effectively. But SAT polynomial time reduces essentially at that point to any problem. And the reason is because make your reduction just compute, it just runs, it simulates the algorithm that checks whether or not SAT is in P. So like the reduction would be as follows. So suppose SAT has an algorithm A that checks if a given SAT instance is satisfied, like a Boolean form. Then my reduction, if I want to map some problem in SAT to a problem in max flow, I can just run the algorithm A. I just simulate A. If the given formula is satisfiable, so if we'll call it phi. Phi is going to be the formula. This is like a SAT formula. If phi is if A tells me that phi is satisfiable, then map to some instance where the max flow is the answer is yes. you just output a graph where the max flow condition is satisfied. And if not satisfiable, satisfiable, just do the same thing, but make it so the max flow is like doesn't exist basically. There's no max flow that satisfies the condition. It has absolutely nothing to do with max flow specifically. The key is that any problem that's in P, if you have any problem that's in P, the entire notion of polynomial time reductions kind of makes no sense. Because if you can solve the problem in polynomial time, reducing in polynomial time, you can just solve the problem in polynomial. like essentially you're saying that up to polynomial factors, SAT is less hard than max flow. But if SAT is already in P, then you could reduce it to anything in like constant time. Like if this just is any problem that has yes instances and no instances, you can just solve the problem with the reduction. Like it's kind of silly, but yeah. So if you're ever wondering like why don't we talk about polynomial time reductions when we're talking about like greedy algorithms or like anything like that, it's because polynomial time reductions only make sense for things that aren't in P. Like, yeah, if something's in P, everything just kind of falls apart. Yeah. So what you said for 3 is like important for this problem. Yeah. Yeah.
Just can you explain it again? The solution.
Yeah. So if you have a polynomial time algorithm for SAT, I can create a reduction from SAT to basically any problem, like literally anything. Like you could even reduce it to the simplest problem you could possibly think of, where like I give you a bit, a single digit, and if it's a 1, you answer yes, and if the answer is 0, you answer no. You can do it. It's a constant time algorithm. You can reduce SAT to that problem. How could you do it? By just your reduction is to simulate the algorithm A that checks if a given formula is satisfiable, and then just output an instance of the other problem where the answer is yes, or output where the answer is no, based on what the response you got from A. Yeah.
We're reducing SAT to some other algorithm. I don't understand why we're outputting max flow. Like, aren't we trying to solve SAT?
But that's what a reduction is. A reduction is a mapping from problem instances from here to problem instances here. And there's 2 things that have to be satisfied. The reduction has to take place in polynomial time, because it's a polytime reduction. And second, the yes instances and no instances of both of these have to be in correspondence. Like, I have to map yes instances to yes instances and no instances to no instances. Yeah, that's the key. So as long as the problem over here has sometimes the answer is yes and sometimes the answer is no, you would get a polynomial time, which is really strange. Like, what it means is that if P is equal to NP, then everything in P and NP complete, they all polynomial time reduced to everything else. Yeah, which is, that would be surprising. That's one of the reasons why like people generally don't think that P is equal to NP. You would get a lot of really strange results. Okay, cool. Let's do another reduction. This is a good reduction. 5. This is the 0 weight cycle problem. So this is also in the book. Maybe I will. So if anyone wants to get a picture of this, go ahead. undo problem 5. So it says you're given a directed graph G and weights on its edges E. And the weights can be negative or positive. And the 0 weight cycle problem is to decide if there's a simple graph, a simple cycle in G. So the sum of the edge weights is exactly 0. And prove that this problem is NP complete. So 0 weight cycle. ZWC. So you're given the graph G. And some edge weights. Decide whether, it's pretty straightforward. Decide whether there is a 0 weight cycle. The sum of all of the weights in the cycle is 0. I think that there are two, okay, so like the first thing in any reduction problem is like you pick a problem that you're going to try and reduce to. I suppose you could always start by proving that it's an NP. So maybe we can start by doing that. So step 1, prove ZWC is an NP. So how do I argue that this is an efficiently verifiable condition? What are the things that I can check? And also, what is an input? So like what are the potential solutions to this problem? So you're already like given the graph. You assume that the graph isn't part of the verifiable like piece. You already have that. What is the solution look like? Yeah.
Should you first check if there's like if a simple cycle exists in the first place, or is that assumed?
You could. I think so. Yeah. Check if there's a simple cycle exists. Yeah, you could. You could do that in polynomial time, right? Like we already know how to do cycle detection in polynomial time. So if you wanted to check, I think that would probably more come like in the second piece maybe. But like right now, we're very narrow focused, where all that we have to do here is, given a potential answer to this, determine whether or not that solution works. We don't really care. Like if we find out that, oh, there's no cycles, then we know the answer is no. But if the answer is yes, if there are cycles, that doesn't really help us. Like we still have to just go back and check the given solution. So yeah.
I guess the solution would be like a list of nodes that traverse.
Okay. Yeah, sure. So it would be like a path or a cycle. Yeah. So it would be a list of nodes. Maybe you could even say a list of edges. Like I would have also accepted if you wanted to say a list of edges, that would also work. It's just encoding the same information, right? Because if I start at VI1, if the next vertex is VI2, then that means that the edge I used was the one between VI1 and VI2. So yeah, so this works. Okay, so I know the input that I'm going to be given is a sequence of nodes, basically. And this is going to determine like a potential cycle. So then what else do I have to check?
Check.
If my input is the nodes, what should I check? Yeah.
You should check that it starts and ends at the same.
Right. Yeah. So we should check like maybe does VI1 equal VIK? Is this an actual cycle? Okay. What else should I check? I think we should probably check, like, we should make sure that these edges exist. You know, like, there are certain things that we should check. Okay, so maybe check if ij vi j plus 1 edges exist. So if you give me a list of vertices, I should check that this is kind of all checking to make sure that this is actually some cycle in the graph. And then finally, what? So let's write something else.
At the edges.
What? Oh,
At the edges.
to make sure what? Yeah, we should make sure that these edges, maybe actually I can just group it in with this. Make sure that these edges exist and that they add to 0. Exactly. So I'm just like usually the things that you have to check. This is why usually these are the easy parts. It's just you just go based on the problem, right? This is the 0 weight cycle problem. So given a potential solution, I'm just checking if it's a cycle, and I'm checking if it's 0 weight. Like I'm just kind of going on the list of things that need to be satisfied, essentially. Okay. Is everyone comfortable with this justification that's in NP? Yeah.
So that like first stuff like checking if VI subset 1 is to
Yeah.
VIK.
Yeah.
That's like basically the more specific way of saying like check if the cycle exists.
Right. Yeah. I'm just making sure that these two nodes are in fact like the same node. That as you're going around, like you eventually do in fact come back to the same node. Yeah.
So when like in an exam, you have to make sure to first give exactly be very specific what your input is, like whatever is set or whatever.
I think that's best practice. I think that's the most clear is saying like, okay, we're given this input. Now I'm going to verify this input. Like it'll make Aaron's job easier because he'll know that you either know what you're talking about or you don't. If you don't want to phrase your proofs like this, that's okay. It's just I think this is a very clear way of doing it. Okay, cool. Now let's I'll leave this here. Now we need to do some. Oh yeah.
Yeah, just a question. So on the second step, is there only 2 edges, or is it what the parentheses? What
Yeah.
are
This
parentheses?
would be like for all j.
Oh, okay.
So I need to make sure that like this edge exists and this edge exists and this edge exists all the way down, and then I also need to make sure that they all add up to 0. Yeah. Yep. Okay. So now I need to prove essentially that so again, every proof, I prove that it's an NP, and then I prove that it's NP hard. That's what it takes to prove something is NP complete. So I need to pick something to reduce. So again, which side of this inequality does ZWC go on? If I'm what? Right side. If I'm reducing, if I'm trying to prove that this is NP hard, I'm trying to prove that it's hard. So it's on the hard side. So I'm going to reduce some NP complete problem to ZWC. And I think that there are a couple of choices for this. I think there's a couple of reasonable choices based on the problem, and I have 2 different proofs. So yeah,
It's one subset.
one of them is subset sum. So this is, I would say, pretty kind of comparable to the homework problem with the Hulk. You guys were working on the traveling Hulk or whatever. You can do it that way. So okay, so let's do subset sum. Do you have a reduction in mind, or you just kind of you felt like it was subset sum, so you did subset sum, which is fine. Yeah. Oh, cool. Yeah. Subset sum works. There is a reduction from subset sum. Does anyone have any other suggestions?
Can you do is this graph? Can you do directed Hamiltonian?
Yes. So the other solution that I have is for directed Hamiltonian. So great. Okay. what made you pick direct Hamiltonian cycle?
Because
Just to give intuition to the rest of the class, like if you were struggling, like what problem to use, like what about this problem made you think that?
I kind of have like a reduction where you just like basically you just make all nodes that would go back to the start be like negative n-1 weight, and then you make all the other edges 1 weight. So the only way to get back to the quote start is
I agree. Yeah, that is my solution as well. But I think like I kind of want to focus on like the intuition part first. Like so, definitely I think Hamiltonian cycle jumps out because it's a cycle problem, right? Like if you ever see a cycle problem, I think it's reasonable to try and hit it with Hamiltonian cycle. Hamiltonian cycle is like the one NP-complete problem that we know. That's a cycle problem. It's also a graph problem. What about subsets now? Like maybe do you have any? Oh, was it from the homework? Like, did you feel like it was similar to the homework?
Yeah,
Or
can you just like make the, I guess,
yeah, but I don't want the reduction. I want like what about this problem made you think subset sum?
add to a certain number?
Yeah, thank you. Yeah. So like the fact that it's adding to exactly one value, that is the way subset sum works. Subset sum, you're given a set of integers and you're asked, is there a subset that adds up to exactly k or whatever? And this also has this property, right? Where the edges have to add up to exactly 0. So I think that is like the similarity between subset sum. So if you were like, I think if you're trying to build intuition of like, how do you figure out which problem to use, there are these certain properties, like cycles, adding up to a specific value, or these like constrained optimization problems, these patterns that NP-complete problems have, and you just kind of want to pick like the closest cousin to the NP-complete problem that you're dealing with. So, okay, great. I think Hamiltonian cycle, especially because it's different than what was on your homework, is what I will do for my reduction. So I think I'm going to do Hamiltonian. Okay. And we're going to follow exactly what Eric suggested. So this means that we're given a graph. In the Hamiltonian cycle problem, we're given a graph G. Are the edges weighted or unweighted? Hamiltonian cycle problem. Unweighted, right? These are actually unweighted edges. And so we're going to have to add weights to them. And what was your suggestion?
just do 1.
Okay, so you have a graph. Maybe pick a node and make. So we're given this graph G. Maybe we'll make a new graph. G prime. And this is going to be the graph. This graph is what we're going to use for CWC. So G prime will have some edge capacities. And you're saying to make these 1 for the most part.
Yeah, for the most part.
And which edges are not going to have capacity 1?
The edges that point towards your start node, or like you have to designate some start node.
Okay, does it matter which one we use?
It does.
Yeah, it doesn't. Okay, so just pick some. A Hamiltonian cycle is really just kind of like a loop in the graph. So any of the nodes could be considered a start node. So pick a start node. Now make the capacity of every edge equal to 1, except edges pointing to V start. So you might have some edges that go out of V start, but eventually there'll be some also nodes pointing into V start. And what should we make these edge capacities. What was your suggestion?
It was like negative rapid and
Okay, so I've made all of the edge capacities 1, except for the select few nodes that are pointing into some starting node. And I've made those negative n minus 1. Okay, someone, not Eric, because this was his solution, tell me like why. What's the, someone predict my next step. Why does this all of the sudden like connect Hamiltonian cycles and zero-weight cycles? Yeah.
Because you don't want to repeat the node.
You don't want to repeat what?
You don't want to repeat the node.
Okay, yeah, I agree you don't want to repeat the node. Certainly.
So is that why you think wait to start 1?
Okay, maybe we should does everyone agree that this reduction can be done in polynomial time? Like I can build G prime in polynomial time. Okay, so let's just make note of that. So we can build G prime. This means that our reduction is computable in polynomial time. That's the first condition. Like all of our reductions, they have to be computable in polynomial time. That's good. Because all we've done, we haven't even changed the graph at all. All we did was just add like edge weights. So really, really easy. Polynomial can be like just size of number of edges. Okay. So we can build G prime in polynomial time. Now all we have to do is argue that a zero-weight cycle exists in this graph if and only if a Hamiltonian cycle exists in G, right? We have to prove like the equivalence of solutions to the Hamiltonian cycle problem for the original graph and the zero-weight cycle problem in our new graph. We have to prove both directions. So let's start with one direction. So this is like what we were talking about earlier in class, of like proving both directions of the if and only if. So like, suppose there exists a Hamiltonian cycle in G. I'm proving that if there's a Hamiltonian cycle in G, then there's a zero-weight cycle in G prime. Right? That's one direction of the implication. Someone tell me why, if there's a Hamiltonian cycle in G, why there's a a zero-weight cycle in G prime. Someone tell me why.
I feel like this is kind of silly, but I feel like if there's a Hamiltonian cycle in G, and we know G prime is already a Hamiltonian cycle, but we know G is going to be a zero weight, then we can get the result that the other one's also probably going to give us zero weight.
It will definitely give us a zero weight because a Hamiltonian cycle has how many like edges or nodes? It's all of them, which is n. Like a Hamiltonian cycle, it's a cycle that covers all of the nodes. And similarly, it will also use n edges.
And it only visits them once, right?
Yes. Yeah, so Hamiltonian cycle, it's a cycle throughout the graph, and it visits every node exactly once. So part of that is that it visits it once. The other part is that it's every node.
Yeah.
So, right. So if there's a Hamiltonian cycle in G, there's also a Hamiltonian cycle in G prime. Trace it, it will have n-1 edges leading up to V start, and then it will have to finish by going into V start. So there's n-1 edges with capacity 1, and 1 edge with capacity negative n-1. So suppose there's a Hamiltonian cycle in G. the same cycle exists in G prime, and with, yeah. So I said that there are n minus 1 edges with capacity, just 1 second, yeah. With n minus 1 edges with capacity 1. And 1 edge with capacity minus n minus 1. Question?
Sorry, I didn't understand the negative n minus 1.
Uh.
Is it that for all the integrate edges for the start node, they have n minus 1?
Yes.
Okay.
So the idea is that any cycle, it will have exactly 1 edge that goes into V start. So if I have a Hamiltonian cycle and has n edges, only one of them will have weight minus n minus 1. The rest of them will just have weight 1. So a Hamiltonian cycle in G, when I port it over to the world of G prime, becomes a 0 weight cycle.
Is that a characteristic specifically of the Hamiltonian cycle that it only has 1 going back to start? Or is that just
Correct. Like any Hamiltonian cycle, because like a Hamiltonian cycle at the end of the day just looks like a loop. There could be extra vertices. Or sorry, there could be extra edges in this graph, but at the end of the day, a Hamiltonian cycle just looks like this. So every node has exactly 1 in edge and exactly 1 out edge. So if I look at V start, it'll only have a single edge in the Hamiltonian cycle pointing in. All of the rest of them will be capacity 1 edges. Okay. Final step. So maybe I'll argue for time. Oh, argue for time. I said a minute. So again, if you needed to go, that's completely fine. If you want to stay, the rest of this is to prove that, okay, if there is a 0 weight cycle in G prime, then there's a Hamiltonian cycle in G. So the way we would finish this off is suppose there exists 0 weight cycle in G prime. How would I argue that there must be a Hamiltonian cycle in G? How do I argue that the 0 weight cycle in G prime already is a Hamiltonian cycle? So okay, so like one problem is that like the 0 weight cycle problem doesn't say that you have to use all the nodes. It could just be a small cycle. It could be like a 3, I don't know, something small like this. This is a 0 weight cycle with three nodes. It could be like somewhere in the graph there's just something small like this. Why can this not happen?
Because the only edges that contain negative values, which is the only way you get to 0, if you have every edge is a positive.
Exactly. Right. The only edges that are negative are the ones with minus n minus 1. And if you use one of those edges, it means that you had to use n minus 1 of the other capacity 1 edges, meaning that you had to have used n edges in total, right? So I'll try and write that as clearly as I can, but that's the gist of it, is that you must use, it must contain, this 0 weight cycle must contain at least one minus n minus 1 weight edge. Because it's 0 weight, so it has to contain at least one of the negative weights. Similarly, because it's zero weight, then to be zero weight, it must have n minus one edges. And if it uses n total edges and it's a cycle, then it must be a Hamiltonian cycle. Cool. Yeah. If you're curious, you can always do the subset sum reduction. That's also a good reduction. If you did that on the exam instead, that would be perfectly fine. Otherwise, good luck. I might stick around for an extra just like 10 or 15 minutes if you guys have any last minute questions. But other than that, yeah, good luck tomorrow. I will not see you, unfortunately, but have a good summer otherwise.
Will the professor be sheltering the exam?
I have a question. So does this apply for like directed graphs as well? Like
Everything is here is directed.
oh okay, so
Undirected-
I meant like undirected, so where it can go like either direction. Like how you said that there would be like only like one specific like negative and minus one edge. That wouldn't
Yeah.
Yeah, this proof would not work.
Yeah.
You can just go to
It may still be empty.
you can just try to
Try to find a path.
That works.
Yeah.
yeah, and then you would have
And you
like
go back and then you have a negative edge.
Jack,
No, I think, wait. No.
send you a test request.
Yeah, okay. Sounds good. Does that answer the question?
It did,
I don't
yeah.
know. If you look at the undirected version of this, I don't know. But I know that this proof won't work.
Yeah. Yeah,
That-
I
that
was
was
just
your
wondering
question,
about that. Okay.
Let me get him first.
I was gonna ask, so I think I missed it then. What was your justification for why we're not gonna get cycle that like jumps up to the nodes and like doesn't reach all of the nodes?
So if you don't use any negative edges, you won't have a zero weight cycle.
Right.
If you do use one of the negative weight edges, you have to compensate by using n minus one positive edges to get yourself back up to zero. If you use n total edges, then you've hit all the nodes.
But could we visit, oh, I mean,
Cycle is no repeated
okay, so
nodes. So it's not a circuit. Yeah, it is a cycle and not a circuit.
So is there gonna be like a accountability problem tomorrow?
Accountability. Yeah, we didn't get to that today. There could be.
There could be, okay.
It won't be a big part of the exam. Like it won't be like a free response. Like it could be like a multiple choice or something.
And there,
If you guys want to go over accountability really fast, like I can.
so there will be about like 6 questions ish from
I mean, like with subparts and like all of that stuff. So it's like it's kind of hard to.
okay.
It's hard to say that there's just like 6 because if there's one question with 2 parts, then 2 questions, or is it 1 question? Up to you to decide. I don't know.
Okay.
Like if I tell you there's 6 and then up to your definition there's not 6, then you're gonna be mad at me. So
Okay.
I don't want you to be mad at me.
But there's 6 like
You
once
can
do
complete it
something-
in a reasonable amount of time. It is designed to be completed in a reasonable amount of time.
Okay.
Yeah. Like yeah.
So there's 6 questions, but a lot of them.
I didn't say that. I did not say that there were 6 questions.
My question was, how focused is the exam going to be on NP and T?
How much?
Yeah, like the weight.
Majority.
80% of it.
With the right numbers.
Always love.
You and points or I mean I don't know. Like the main topics are stuff that like was covered near the end of the course. So like
Flow and NP. Okay.
I would say the big topics in order are P, NP, complete stuff. That's number 1. I would say that comprises at least 50%. Then like there's maybe a small amount of like the new stuff, the really new stuff that you've done, like the undecidability, but like probably more so in like the multiple choice section, like smaller, just like
Oh, there's a multiple
easier.
choice section.
there is a multiple choice section. I will tell you that much. And then there could be like a couple problems, like one or two on like DP, greedy, like those were topics that we spent a long time on. I think it's fair to expect like at least one good problem on like those. I don't know. I mean, like what would you, if you were writing the exam? That's probably what you would put on. Like you'd hit all the main topics, right? Like
No, I was
it shouldn't be a mystery
so
what's on
there's
the exam.
one of
like,
each, like DP, greedy.
Yeah, I mean,
like one of each,
it's yeah,
at least.
it's a final exam. Like you should expect like
Not accept that.
some number of like testable questions like from all of our main units, I think. But yeah, it is. I would say still the heaviest section is on NP completeness, reductions. It's a big part of the exam.
What's the difference between a cycle and a simple cycle? I don't know. You don't know, okay.
Yeah, probably simple cycle is said to specifically make very clear that it's not a circuit.
Okay.
Like usually anymore, I feel like if I'm reading, circuits are potentially repeated nodes but not repeated edges, and cycles are no repeated nodes. A simple cycle makes it very clear that you're talking about what I just described a cycle to be.
Should we expect problems of countability similar to the ones you gave us in the discussion?
In here? Yeah, I think they're about as hard. They may not be like exactly the same form,